Good afternoon, all of you. We will continue with entropy. So last class, what we saw was the entropy of the universe always increases. Your entropy of the universe can never decrease. It should increase to the maximum. It can remain constant. It should either increase or it should remain constant. Okay. And this increase in entropy principle, we can see that there are a lot of applications which which works on the increase in entropy principle. Okay, so every irreversible process, it is accompanied by the increase in entropy. So whenever there is an irreversible process, your entropy increases. So we have seen that at Cauchy's inequality. Okay, Cauchy's inequality, we saw that cyclic integral of dq by t is less than or equal to 0. Okay, and the converse of this is we can say delta S is greater than or equal to 0. So your delta S is equal to 0 when the process is reversible, and it is greater than 0 when the process is irreversible. Okay, and when delta S of the universe is less than 0, then that becomes an impossible process. We have seen this in the previous class. So whenever you have an irreversible process, your entropy always increases. Okay, and depending upon the value of that entropy change, say if delta S for one process is say 5 kilojoule per Kelvin, just for an example. Okay, so for one process, the entropy changes 5 kilojoule per Kelvin. And for another process, the delta S is 500 kilojoule per Kelvin. Say for here, the delta S is 500 kilojoule per Kelvin. Okay, obviously this 500 is very much greater than 5. So depending upon the value of the delta S, the irreversibility of the process can also be defined. So the process where your delta S is 500 is more irreversible than the process where the delta S is just 5 kilojoule per Kelvin. So higher the change in entropy, higher the irreversibility of the process. Okay, so when the delta S value is high, we can understand that the process is highly or more irreversible. Okay, and there are a couple of examples that we can go through. So one such example is transfer of heat through a finite temperature difference. Okay, so this is not a heat engine. There are two reservoirs. One is at a higher temperature T1. The other reservoir is at a relatively lower temperature T2. Okay, and we know that heat always flows from a high temperature region to a low temperature region. Okay, so heat is going to flow from reservoir A to reservoir B, maybe through a channel which is shown here. And because of the steady state, there will not be any change in entropy in this particular channel. Okay, but what you can note is this reservoir A is going to lose heat, and this reservoir B is going to gain heat. Okay, so if Q amount of heat is leaving T1, Q amount of heat is going to be gained in the reservoir B. Okay, but the temperatures are going to be the same. The temperature is still going to be T1. Here the temperature is still going to be T2 because they are reservoirs. Irrespective of heat added or heat lost, the temperature of the reservoir is going to remain the same. Okay, so here if you consider this, so this is for reservoir A, so they have considered it as delta S A. What will be the change in entropy A? So heat is lost. So you should give a negative sign. So it is minus Q divided by the temperature of the reservoir. So it is minus Q by T1. The change in entropy for reservoir B, that is going to be Q by T2. And that Q will be a positive term because heat is entering the reservoir B. So that is plus Q divided by T2. So what is, so you can see because heat is lost. So here this change in entropy is negative. Okay. And because heat is added, here the entropy change is positive. Okay. So when heat is lost, you will have a drop in entropy. When heat is gained, you will have a gain in entropy. Okay. But both of them together, if you are adding it, this fellow should be greater than zero, or at most it should be equal to zero. That is what we have seen from the converse of Cauchy's inequality. So delta S of the universe will be delta S A plus delta S B. Okay, so delta S A is minus Q by T1 plus Q by T2. So Q into, so if you take LCM, so it will be minus Q T2 plus Q T1 divided by T1 T2, and you will have Q into T1 minus T2 divided by T1 T2. T1 T2. That will be the entropy change of the universe. Okay, and if T1 is greater than T2, what do you mean by T1 greater than T2? If T1 is greater than T2, the delta S will be positive. If T1 is greater than T2, delta S will be positive, which means it will be greater than zero. So if delta S is greater than zero, then that is an irreversible process. So if T1 is greater than T2, what you have is irreversible process. Okay, so this fellow, if T1 is greater than T2, is going to be irreversible. What if T1 is equal to T2? That will become zero. So delta S is equal to zero. When is delta S equal to zero? When the process is reversible. Okay, and if T1 is less than T2, that will make this delta S negative, which makes the process impossible. You can't have a process where the entropy change of the universe is negative. That is not at all possible. So this is impossible. Okay, so these are some of the inferences that you can have from the transfer of heat through a finite temperature difference. Okay, and the key is it is a reservoir. So that is something you should keep in mind. Okay, and another example is mixing of two fluids. Okay, so I'm taking a container and I am dividing it into two subsystems, subsystem 1 and subsystem 2, by a partition. So there is a partition here. So you can see that there is a partition here. So I am dividing subsystem 1 with subsystem 2. So in the subsystem, the amount of mass is M1 and the heat capacity of whatever is present is C1, and it is at an initial temperature T1. Okay, and in the subsystem 2, the mass of the substance is M2, its specific heat capacity is C2, and its initial temperature is T2. Okay, so I have kept it in an adiabatic enclosure, which means no heat is entering into the system, no heat is leaving the system. And from the diagram, you can also see that no work is done on the system or no work is done by the system. So there is neither heat transfer nor work transfer. There is no energy transfer here. It is like an isolated system. Okay. Now what I'm going to do is I am going to remove this partition. This partition is being removed now. So if I remove this partition, these two fluids are going to be mixed. Okay. And what we can see here is T1 is greater than T2, which means the subsystem 1 is at a higher temperature and the subsystem 2 is at a relatively lower temperature. Now, when both of them are mixing, they should come to an equilibrium temperature. Okay, both of them are mixing, they should come to an equilibrium temperature, and we call that as TF, F for final. The final temperature should be an equilibrium temperature. T1 should come down and T should go up, and both of them should come to an equilibrium temperature. So that is what we call as the mixing of two fluids. Okay, and we have, this is like uh, so once it gets mixed, okay, so This is once again an irreversible process. Okay, when the equilibrium temperature is attained, so then you have to do another process to separate them. Again, you have to follow so many uh, other methodology to separate these and bring them to its original state and to their initial states, and that is going to be impossible. Okay, so this is also an irreversible process. So what we see here is this TF is going to be between T1 and T2. Okay, so T2 is lesser than TF, which is lesser than T1. Okay, and what we see is because this T1 is greater than T2, whatever substance is there in the subsystem 1 that is going to lose heat, and whatever heat is lost by the subsystem 1 that is going to be gained by the subsystem 2. Okay, while mixing, this substance in subsystem 1 is going to lose its heat, and that substance in subsystem 2 that is going to gain the heat which is lost by subsystem 1. Okay, and how far this temperature is going to be lowered? This T1 is going to be lowered till it reaches TF. How far this T2 is going to gain heat? Till the temperature reaches TF. Okay, so if you write the heat transfer for both the subsystems, you will get an energy balance which is MCP delta T. So M1C1 into T1 minus TF, which is equal to M2C2 into TF minus T2. Okay, TF is greater than T2, so it is TF minus T2. Here T1 is greater than TF, so T1 minus TF. So if you expand this, open the braces and expand it, you will get this particular equation here. Then you can bring the TF terms. You have two TF terms. You can bring TF terms on one side, so which means you will get M2C2 TF plus M1 C1 TF, and this is equal to M1 C1 T1, M1 C1 T1 plus M2 C2 T2. So this is plus M2 C2 T2. And now you can take this TF as common here on the left hand side. So if you take this TF as common, you will get M1 C1 plus M2 C2 into TF, which is equal to M1 C1 T1 plus M2 C2 T2. And so you will get TF as M1 C1 T1 plus M2 C2 T2 divided by M1 C1 plus M2 C2. So that will be the final equilibrium temperature that you will get when both the fluids are mixing. Okay, and just like the previous case, here one subsystem is going to lose heat and the other subsystem is going to gain heat. That which loses heat is going to have a negative entropy change, and that system which gains heat is going to have a positive entropy change. So delta S1, as per definition, it is integral of dq by t, and the limits is going to be the initial state is T1 and the final state is TF. So you have T1 to TF dq by t, and that is supposed to be a reversible path as per the definition. So we write it as dq reversible by t, and we have already seen that an irreversible process can be replaced by a reversible path that we have seen in the previous lecture. Okay, so here we can replace that dq with m1c1 dt divided by t. M1c1 is constant, which can be taken outside the integral. Integral of dt by t is ln of t between the limits t1 and tf. So upper limit minus lower limit, ln tf minus ln t1. Using logarithmic rule, you can write it as ln of tf by t1. Okay, so you get this particular term m1c1 times ln of tf by t1. And because the subsystem 1 is losing heat, this particular delta S1 is supposed to be negative. Smaller term divided by a bigger term inside the logarithmic natural logarithm will give you a negative value. So delta S1 will be negative. Okay. And delta S2, similarly, you can find it in a similar way. So here the initial state is T2 and the final state is TF. So the limits are between T2 and TF. So when you integrate it, you will get M2C2 ln of TF by T2. So now to find out the entropy change of the universe, you have to add them. That's all. And this fellow should be greater than 0. And if it happens to be reversible, at most it can be equal to 0. It can never be less than 0. Okay. And if we consider that the value of the mass of both the subsystems are same, if M1 is equal to M2, and if C1, if both of them are having the same substance, having the same specific heat capacity of air is going to be 1.005 kilojoule per kilogram Kelvin. Say I have 1 kg of air in both the subsystems, then I can replace M1, M2 with M and C1, C2 with C. And if I do that, so what I will have here is, so this particular equation, we can replace this and write it as, so this equation we can write it as MC ln of TF by T1 plus MC ln of TF by T2. We are replacing M1, M2 with M and C1, C2 with C. And once we do that, now we can see that MC is common in both these. So this further becomes MC times ln of TF by T1 plus ln of TF by T2. See, here also you have addition of two logarithmic terms. So according to the logarithmic rule, if you have addition of two logarithmic terms, they can be multiplied. So what you have is ln of TF squared by T1, T2. Okay, so that is what you get here. MC ln of TF squared by T1, T2. So logarithm x plus logarithm y. Ln of x plus ln of y will give you ln xy. So similarly, you have ln TF squared by T1, T2. Okay. And further, this can be converted into this term from this particular relationship. Okay. So let me use another color here. So now that if M1 is equal to M2 equal to M and C1 equal to C2 equal to C, I can write this as MC T1 plus MC T2 divided by MC plus MC. Okay, what you will have here is MC can be taken as common, MC into T1 plus T2 whole divided by 2MC. Okay, I can cancel out this MC and MC here, and you will get this TF as simply T1 plus T2 divided by 2. So you can replace this TF with T1 plus T2 divided by 2 and the whole squared. Okay, so what you will have here is, so if I replace this term, so what I'll have is MC ln of, so instead of TF squared, what you'll have is T1 plus T2. So within the braces, whole divided by 2 and even this whole term is squared, T1 plus T2 divided by 2, the whole squared, divided by T1, T2. Okay, I don't have space here. And you can take this 2 to the front, so that becomes 2mc, and you have ln of T1. So if you have to take this 2 here, then that should be a common square, so that this fellow is also root of T1 by T2. So if you make this as root of T1 by T2, then you can take the whole squared for the entire term. Now the square is only in the numerator, so to stretch it to the denominator, so you have to write this as I'll write it here. So you have to write this as mc ln of T1 plus T2 divided by 2 whole divided by root of T1 T2, and this entire term is squared. So now if this entire term is squared, comprising both the numerator and the denominator, now this 2 can be taken before or outside the ln, so it becomes 2mc ln of T1 plus T2 divided by 2 whole divided by root of T1 T2. Okay, so that is what we get. This is nothing but a mathematical relation that you get for mixing of two fluids. Okay, this is another example. So similarly, we have two more examples under this particular category. Okay, the other one is maximum work obtainable from two finite bodies at temperatures T1 and T2. These are our examples. We are looking into the applications. Why we are looking into the applications is just to have a variety of applications wherein you can understand the concepts of how entropy is being affected or how entropy transfer takes place. Okay, so now what we have here is I have two bodies, one body at temperature T1 and there is another body at temperature T2. And if both of them are brought into contact, if they are just brought into contact without any work transfer, I'm going to talk about two conditions here. The first condition is body 1, which is at a temperature T1. Obviously, T1 is greater than T2. That is obvious. Okay, I am having a body at temperature T1 and I have a body at temperature T2 without any work. I'm just bringing both of them into contact, physical contact, so that a thermal equilibrium is attained. Just like the previous case, when I broke the partition, both of them mixed. One was at T1, another was at T2. When they mixed, they reached a temperature TF. Similarly, now I am bringing both the bodies into a physical contact so that heat transfer can take place from the high temperature body at T1 to the low temperature body at T2, and both of them come into a equilibrium temperature TF, which is the final temperature. And this is just physical contact. No work is done here. In such a case, this would be the formula for estimating your TF, T1 plus T2 divided by 2. When two bodies are brought into contact with no work input, so TF will be the average of T1 plus T2. This is very simple. You can imagine that this T1 is at 50 degrees centigrade and this fellow is at 30 degrees centigrade. And common sense tells us that this 50 should climb down to 40 and this 30 should also climb up to 40. So this loses 10 degrees centigrade of temperature, and that 10 degrees centigrade is gained by this body so that both of them are at 40 degrees centigrade. And how do you get it? Just take the average, 50 plus 30 divided by 2. 80 divided by 2 is 40. Okay, so when no work is done and just a thermal contact is established, your TF is just the average of the temperatures of both the bodies. Okay, suppose I want to find the lowest attainable final temperature so that maximum work is delivered. Okay, so if for this case, when 50 degree is brought to 40 and this 30 is brought to 40 without any work done, okay, it was just thermal contact, so no work is being done here. Okay, and when it goes from 50 to 40 and this goes from 30 to 40, some amount of work could have been done because there is a temperature difference. Whenever there is a temperature difference, you can operate an engine. But the moment both the bodies are attaining equilibrium temperature, then the engine stops operating. So here it starts with 50 degree, it is supplying heat, some amount of work is being delivered, some amount of heat is rejected. And because of this, this T2 is rising. Say this T2 has raised to 35. Okay, just for an example, this T2 has raised to 35 and this has come down to 45 degrees centigrade. Still you can run the heat engine because there is a temperature difference here. Okay, and it was delivering work. Now this has come down to 40 and this has also gone up to 40. Can you now run an engine? You can't run an engine because there is no temperature difference. Both of them are at equilibrium. When there is no temperature difference, there cannot be any heat transfer. There will not be any heat supplied. There will not be any heat rejected. Okay, so only when there is a temperature difference, you can have the heat transfer. So your engine will operate only up to this equilibrium temperature. Only up to this equilibrium temperature, or to say precisely, your engine will function till it reaches the equilibrium temperature along with the sink. Okay, so now let me find out, or what we try to do here is, let us find out the value of TF such that maximum amount of work is being delivered. Okay, so we know that Q1 is the amount of heat that is supplied by this body 1. Okay, and your engine is going to function till it reaches TF. So your Q1 will be Cp times T1 minus TF. Okay, and Q2 is going to be Cp times TF minus T2. Okay, so what is the work done? Work done is Q1 minus Q2. The amount of heat supplied minus amount of heat rejected will give me the work done. So you, by simply opening the brackets, so Cp times T1 minus Tf plus Cp times Tf minus T2, you will get Cp times T1 plus T2 minus 2Tf. Okay, and what that is the total work done that you have. And what is the change in entropy for this body 1? That will be negative because you are losing heat. Okay, Cp times ln of Tf by T1. We have already seen this in the previous case also. So this is simply dq by t, integral of dq by t. So here Q1 is Cp times T1, so Cp times dt. So Cp times dt by t between the limits T1 and Tf will give you Cp ln of Tf by T1. I hope this is clear to you. In the last example also we saw something like this. Delta S2 is the entropy change in the sink. So that is between the limits T2 and Tf. Cp times dt by t will give you Cp ln of Tf by T2. And we know that the entropy change of the universe should be greater than or equal to 0. Okay, and what is the entropy change of the universe? It should be Cp ln of Tf by T1. So entropy change is nothing but delta S. Entropy change of the universe is nothing but delta S1 plus delta S2. Okay, so your delta S of the universe, the delta S of the universe should be equal to delta S of the body 1 plus delta S of body 2. What is the change in entropy in body 1 plus change in entropy at body 2? So this will give you, Cp times ln of Tf by T1 plus Cp times ln of Tf by T2. Similar to what we've done before. So you can take Cp as common and you can multiply those terms within the logarithmic sign. So what you'll have is Cp times ln of Tf squared whole divided by T1 T2. And if you want to remove this 2 to the 2 to the front, then you can say ln of Tf by root of T1 T2 the whole squared. That way also you can write. So this is what we get for delta S of the universe, and we know that this should be greater than or equal to 0. And see, that is what we have seen. So Cp ln of Tf squared by T1 T2 should be greater than or equal to 0. Okay, and we found that the Tf should be as minimum so that your work is maximum. Okay, so for Tf to be minimum, your Cp ln of Tf squared by T1 T2 is equal to 0. Okay, so where will your Tf will be minimum? So let me go to the previous slide. Sorry. So your engine will be reversible. When will your engine be reversible? When your engine delivers the maximum work, and the maximum work is possible when this Tf is as low as possible. That is your Carnot engine. So your Carnot engine is a reversible engine where you have the maximum possible work. So the maximum possible work is attained when the final temperature is as much low as possible. Okay, so for Tf to be minimum, so the Carnot engine is reversible. So we know that this is delta S. Delta S is greater than or equal to 0. Carnot engine is reversible. So for the process to be reversible, delta S should be equal to 0. Okay, so this is delta S greater than or equal to 0. Because we assume the engine to be reversible, so for engine to be reversible, we know that delta S should be equal to 0. Okay. So this is the constraint. And for us, the engine is reversible, so delta S should be equal to 0. If the engine is irreversible, delta S is greater than 0. So we are assuming Cp times ln of Tf squared by T1 T2 should be equal to 0. And by common sense, we know the specific heat value cannot be equal to 0. Specific heat is a number. It should have some value. So Cp is not equal to 0, which means this value ln of Tf squared by T1 T2 should be equal to 0. And when will be ln of something equal to 0? When ln of 1 is 0. So this Tf squared by T1 T2 should be equal to 1. So Tf squared is T1 T2. So Tf is equal to root of T1 T2. So your W will be maximum when your Tf is root of T1 T2. Okay. Previously, what we saw was when no work was done, the value of Tf is T1 plus T2 divided by 2. Now for the work delivered to be maximum, your Tf should be equal to root of T1 T2. So the maximum work done here is, already we have written a formula here. So that formula we are using, W is Cp times T1 plus T2 minus 2 times Tf. So we replace this Tf with root of T1 T2. Okay. And this is nothing but a plus b the whole squared, a minus b the whole squared formula. You will have root of T1 squared plus root of T2 squared minus 2 times root T1 root T2. Okay. So that is root of T1 minus root of T2 the whole square. Okay. So that is what we have here. That is your W max. Okay. So for this particular session, you have to follow me very closely, because all these will be a set of derivations and it will be a set of applications for a particular condition. Okay, so whatever we are seeing, these are not generic formulae or generic equations. These equations are pertain to a particular situation or a particular application. Okay, and we are going through all these because sometimes they ask problems related to these applications. Okay, so we are going through all these things. And one more thing is maximum work obtainable from a finite body and a thermal energy reservoir. If you look at the previous example, what we saw was the work obtainable between two finite temperature bodies. In this case, it is between two bodies. This is body 1 and this is body 2. Now what we are seeing is between one body and a thermal energy reservoir. Maximum work obtainable from a finite body. When I say finite body, a body at a finite temperature and a thermal energy reservoir. So when you say thermal energy reservoir, irrespective of the amount of heat that is being supplied to this reservoir, the temperature of the reservoir is not going to change. The temperature of the reservoir is going to be T naught, irrespective of any amount of heat that is added or rejected. Okay, so that is the advantage of thermal energy reservoir. So delta S of the body is going to lose heat. Okay, and so it is going to lose heat till it attains the temperature T naught of the thermal energy reservoir. So here T is greater than T naught, so it is like a hot object dissipating heat to the surrounding atmosphere, or maybe to a surrounding lake or a surrounding ocean. Whichever it is such a huge thermal energy reservoir. Whatever temperature is lost by the body is not going to affect the temperature of the thermal energy reservoir. Okay, but this body, by losing heat, is going to go from temperature T to temperature T naught. So the initial temperature is T, the final temperature is going to be T naught for this particular body. That is the important difference that you have to note here. In the previous case, here the temperature is T1 and here the temperature is T2. This T1 is not reaching T2. T1 is reaching TF. And here also T2 is reaching TF. Whereas in this particular case, because it is a reservoir, the reservoir temperature is not going to rise. In case of the previous example, this T1 is dropping to TF. Here T2 is raising to TF. 30 becomes 40, 50 becomes 40 here. Okay. Whereas in our example now, this T naught is going to be T naught. Say if this is at 50 and this is at 30, now what is going to happen is this T naught is always going to be 30, no change here. Whereas this 50 is going to reach 30 degrees centigrade. It is not reaching 40, it is reaching 30. Okay, so that is the difference between the heat transfer between finite temperature bodies and heat transfer between a body and a thermal energy reservoir. So now if you look at the change in entropy for this case, so what you will have is Q dQ by T. So that is between the temperature limits T and T naught. The same equation Cp times dt by T. So you'll have Cp times ln of T naught by T. And what is the thermal energy of the thermal energy reservoir? Entropy change of the thermal energy reservoir. So the thermal energy reservoir is going to gain heat. What is the amount of heat it is going to gain? Okay, so Q is the amount of heat supplied by this body. So this is the amount of heat supplied by the body at temperature T, and it is delivering W amount of work. So the amount of heat rejected is going to be Q minus W. Okay, Q minus W is the amount of heat that is rejected by this heat engine. So that is the amount of heat that is entering into the thermal energy reservoir. So here delta S is going to be simply Q by T, and here Q is Q minus W. Okay, so Q minus W divided by T is here T naught. So Q minus W divided by T naught. That is the entropy change of the thermal energy reservoir. So the change in entropy of the universe, you have to add these two. And obviously this should be greater than or equal to 0. Okay, so let me proceed further. So this delta S, which is the change in entropy of the universe, should be obviously greater than or equal to 0. So just like we did in the previous case, this should be greater than or equal to 0. Okay, and what we are trying to find here is the maximum work obtainable. In the previous case, the maximum work obtainable is, any doubts? Someone is unmuted, maybe by mistake. Okay, So in the previous case, the maximum work obtainable was at Tf equal to root of T1, T2. Here, let us find what is the condition for the maximum work that is obtainable. So we know this inequality, and so from this equation, we can write this as Cp ln of T naught by T is greater than or equal to Q minus W by T naught. W minus Q by T naught. Sorry about that. So because this is taken to the other side, so you will have minus of Q minus W by T naught. So that should become W minus Q by T naught. And now it is correct. So W minus Q by T naught is less than or equal to Cp times ln of T naught by T. Okay. And to find out the maximum work obtained, we keep W on one side. So this is taken to the other side. So you multiply with T naught here on the right hand side. So that makes it T naught Cp times ln of T naught by T. And this minus Q is taken to the right hand side. So this becomes plus Q. So your W should be less than or equal to this. And all this is done with a condition delta S universe is greater than or equal to 0. And by our previous study, what we know is your maximum work is obtainable only when the heat engine is reversible. So for the heat engine to be reversible, this delta S universe should be equal to 0. So you can change or remove this less than or equal to and replace with equal to. So your W max is equal to Q plus T naught Cp times ln of T naught by T. Okay. And your heat transfer here is this value of Q is Cp times T minus T naught. So that is the amount of heat that is being transferred from this body to the thermal energy reservoir. Cp times T minus T naught. So that is your Q, and this is the second term. Okay, and you can take Cp as common on the outside, and this is what you get as maximum work when there is a heat transfer between a body with finite temperature and a thermal energy reservoir. Okay, up to this clear? So in all these examples, what we have seen is, in this example, there is a heat transfer. In this example also, there is a heat transfer. In this example also, there is a heat transfer. You can see one is at a higher temperature, the other one is at a lower temperature. So there is going to be a heat transfer. And in the first example, also there is a heat transfer. Here also T1 is greater than T2. Okay. In all the four examples that we have seen, there is a heat transfer between two bodies, bodies or reservoirs, or between a body and the reservoir. We have seen that there is heat transfer. Okay. And this causes entropy change. And now what we are going to see is your entropy change can also be because of some other processes that exhibit external mechanical irreversibility. And we are going to see two examples. Okay. Your entropy change happens because of heat transfer. And now what we are going to see is your entropy change can happen because of irreversibilities. And one example is this isothermal dissipation of work. You see there is a current flowing through a resistor. Okay. And this flow of current can be likened to the work. The flow of current through a wire can be treated as work transfer. And we know that when current flows through the wire gets heated up, and that heat can be lost to the surroundings. So that heat is lost to the surroundings at temperature T. Okay. At steady state conditions, so because no energy is stored here, okay, no energy is stored here. When you write the first law, Q is equal to delta U plus W. So because no energy is stored, Q is equal to W. So the amount of heat that is lost to the surroundings, so delta S of surroundings should be written as Q divided by T. surrounding it as temperature T. Q is the amount of heat that is lost, so that is Q. But because Q is equal to W, you can also write it as W equal to T. Okay. And delta S of the system. What is the system? This resistor over which the current flows. There is no change in entropy here. No energy is accumulated. Okay, so there is no change in the system. So the delta S of the system is equal to 0. So when you talk about the delta S of the universe, you get W by T. Okay, so here your change in entropy is attributed to W by T. Okay, and people call this as isothermal dissipation of work. But this W is equal to Q. That is what is very important. Okay, and why I am telling you this is, in a couple of slides, we will see the relationship or the difference between the work transfer and the heat transfer. Though I call it as W by T, the heat lost to the surroundings is actually Q. So it is actually Q by T, but I can also call it as W by T. We have specifically written it as W by T for a reason. I'll come back to this after finishing the next slide. Okay. One more example here is adiabatic dissipation of work. Okay. So all these examples I have taken from PKNR. Okay. So here, see, there is an insulated vessel which is filled with some sort of a gas or a fluid. And I have a stirrer here and it is perfectly insulated. Okay. With the help of the stirrer, as I am rotating the stirrer, work is done on this gas. Okay, there is nothing else. There is only a stirring work that is happening here. Because of the stirring work, what happens to the internal energy of the gas here? That is going to rise up. This is similar to a situation where you leave your house or you leave your room in a locked condition, closing all the windows and doors, but you have forgotten to switch off your fan. So your fan is actually rotating inside the room. Everything else is switched off and the windows and the doors are closed so that no air enters into the room or no air leaves the room. So as your fan rotates, the temperature of that room is going to go up because the fan is doing some work on the surrounding air inside the room. Such a situation is what we are seeing. So it is, and imagine that the room is also perfectly insulated. None of the temperature is going to leave the room. So that is what is happening here. Because no heat is leaving this wall of the vessel, so there is no change in the surrounding. No heat is leaving the system, right? Perfectly insulated. So Q by T, so Q is 0. So delta S of the surroundings is going to be 0. What about the delta S of the system? So it should have gone from an initial temperature to a higher temperature, right? Initial temperature is I, final temperature is F. So they have said I to F dQ by T. So Cp dt by T will give you Cp ln of Tf by Ti because the temperature has changed from Ti to Tf. So when you add, you get Cp ln of Tf by Ti. And this is where I'm going to show you an important thing, and please try to understand this. The actual process is this dotted line I to F. And this adiabatic dissipation of work is an irreversible process. Okay, because I have switched on the fan and I have left the room. I have kept the windows closed. I have kept the door closed and the temperature of the room has gone up. Okay. And if I have to bring this or make this process reversible, what should happen is the temperature of the room should go down, just like it happens in your magical movies. The temperature of the room is slowly coming down and the fan is slowly rotating in the backward direction. Maybe it rotated, say, some 50,000 rotations it had made, and now there is a 50,000 reversal rotation. And after the 50,000th rotation, it comes to a stop. Okay, and your just leaving the room. It's like a flashback. You would have seen flashback in movies, right? So you are just coming back to the room and you are trying and you are about to close the window. So it should come back like that. And that is not going to happen. So it is purely an irreversible process, just to give you a feel of why we are calling it as an irreversible process. So the actual process is by this dotted line IF. Okay. But my entropy is defined, or we have defined this change in entropy as integral of not any dq by t. This definition is this dq is supposed to be reversible. That is the definition. So even if your process is not reversible, what we have studied is replace it by a reversible path. And that is what I have done here. So the dotted line is the actual irreversible path, or the actual irreversible process. And I am replacing this irreversible process with a reversible path IF, and that is actually an isobaric process. Okay, a constant pressure process where the temperature has gone from Ti to Tf, and it is purely reversible that it can come back from Tf to Ti. Okay, and we can replace this irreversible path with a reversible path. Okay, why I'm telling you this is, see, the work is actually a path function, is it not? Work is a path function. So I am actually replacing this IF, the path IF. If you call this as path A, let me call this as path A, which is an irreversible path. And I'm calling this as path B. So your work done in path A should be different in case of work done with path B. Am I right? Work done in path A should give you a different value, and work done by path B should give you a different value. But now I am able to replace an irreversible path with a reversible path, and I'm able to define the change in entropy. And that is not going to change the definition of entropy, because change in entropy is a point function. Irrespective of the path that is taken, still you have this as Si, and still you have this as SF. Irrespective of the path that is taken, you're still going to have delta S as SF minus Si, final state minus initial state. Okay. And what I want to make you understand here is work transfer does not involve entropy. Your heat transfer involves entropy, but your work transfer doesn't involve entropy. And that is why in the previous slide also I told you, here we are writing it as W by T, but still is it Q by T. And what I am trying to tell you is, though there is a work done in both the cases, here also there is a work in the form of the flow of current. Here also there is a work done in the form of a paddle wheel steering work. But in both the cases, these work done is giving rise to irreversibility. And that irreversibility is contributing to the entropy change. It is not the work done that is contributing to the entropy change. It is the irreversibility that is contributing to the entropy change. I hope you are able to understand this. Your heat transfer contributes to the entropy change. That is very clear, because the definition of delta S itself is dq by t. So your heat transfer is contributing to entropy change. But when you are saying work done, your work done does not have any role in entropy change. It is only the irreversibility that is caused by the work done that causes entropy change. It is only the irreversibility that is causing the entropy change. It is not the work done which is causing the entropy change. Because this path IF should give you a different work done, and this path IF should give you a different work done. Okay. But irrespective of the work that is being done, you're getting the same value for delta S, which means my work interaction does not have any impact on change in entropy. That is very, very important. That is what I want you to understand from these two examples. Though there is a work done here, that work done is contributing to the irreversibility that is arising the internal energy of the gas. Maybe in this particular case, it is actually raising the internal energy of the gas, right? The temperature of the gas is rising. Okay, so that is an irreversibility. The cause may be the work, but that is not contributing to your entropy change. What is contributing to your entropy change is the irreversibility. Okay, and we call that as external mechanical irreversibility. And that is what we will see here also. So just like you have heat transfer and energy transfer, we also have something called entropy transfer. Okay, so entropy transfer can be in the form of heat transfer and mass flow, whereas your energy transfer can be in the form of heat transfer, mass flow, and work transfer. When I say heat transfer and mass flow, energy transfer and mass flow, so in a closed system you don't have mass flow, in an open system you have mass flow. Energy transfer involves work transfer also, but entropy transfer does not have work transfer. Just like heat transfer and work transfer are boundary kind of phenomena, your entropy transfer is also boundary phenomena. Okay, so because there is no mass transfer in case of a closed system. In a closed system, there is no mass transfer. So what is left out is the contribution is only because of heat transfer. So in all our examples so far, we have talked about heat transfer only. That is what I showed you before. So finite temperature difference between two bodies, mixing of two fluids, maximum work obtainable between two finite temperature bodies, and between a finite body and a reservoir. All these are examples of heat transfer interactions. For an adiabatic closed system, obviously no heat transfer, so S is going to be dq by T. Q is 0, so entropy change will also be 0. Okay, so heat transfer, it increases the internal energy of a system. Okay, and as a result of which the kinetic energy of the molecules also increases, and the disorder of the system increases. Say suppose the example is, say you have um, some system. Okay, so in this particular case, I have just shown you the entropy transfer, where from the system heat is leaving the system to the surrounding, which is a temperature T naught. So you can define your entropy transfer as Q by T naught. So that is what the diagram is emphasizing. So for the surroundings, this will be plus Q by T naught. For the system, it will be Cp times ln of T by T naught, whatever the temperature the system is. And if it is trying to attain the equilibrium with the surroundings, so it is Cp times ln of T naught by T. Final temperature is T naught, initial temperature is T. In this particular case, what we are seeing is, say there is a system and there is heat that is entering into the system. So when you are heating a system, what happens to the molecules inside the system? Say suppose I have got so many molecules inside the system. So when as heat is transferred, all these molecules will take that heat energy. Okay, and by taking the heat energy, what will happen to the molecules is their kinetic energy will increase. And when the kinetic energy increases, so kinetic energy is an energy in virtue of motion, which means these molecules can move around with the help of kinetic energy. And as they move around, they will collide with each other. So this collision will increase the disorder of the system. So when entropy increases, the disorder of the system also increases. So your heat transfer does that. So your heat transfer interaction results in an increase in the entropy transfer also. We have already seen that. This is another way of putting forth it. Okay, and this is what I was emphasizing. So there is no entropy transfer with work. Your work does not contribute to entropy transfer. Your work is entropy free. Okay, your work is entropy free. And the example that they have shown here is a flywheel. So your cylinder piston arrangement, your expanding the gas, your gas expansion takes place during the expansion stroke, as a result of which the power is delivered to the wheels. Before it is delivered to the wheels, the power is taken to the flywheel where the energy is stored. So as the flywheel rotates, you get energy from the flywheel for the piston to move for compression. Okay, so So energy is stored in the flywheel. Your flywheel rotates. Okay. So your flywheel rotates. When the flywheel is rotating, the molecules in the flywheel are also put into rotation about its axis. Okay, about the axis of the flywheel, the molecules inside the flywheel, they are also rotating. But all these molecules are in an organized manner. In the previous case, when you took heat transfer, because of heat transfer, the molecules, because they possess the kinetic energy, they move against each other and they collide, and there is chaos in the system. Okay, so that was increasing the disorder of the system. Whereas here in work transfer, all your molecules are also rotating along with the flywheel in an organized manner. There is no disorder here. Okay, so there is no entropy transfer in case of work. And the most important thing which I want to emphasize here is the difference between the first law and the second law. The first law, it simply told you for a cycle summation of Q is equal to summation of W. It treated your work transfer and heat transfer as equals. They are they are the same. They are, maybe you can even say, they are two sides of the same coin. They are equal. Okay, but it is only the second law which makes the distinction very clear. Okay, energy interaction accompanied by entropy transfer is heat transfer, whereas energy interaction where there is no entropy transfer, that is called as work transfer. Take this example of flywheel. Everything is organized. There is no disorder. If there is no disorder, there is no entropy. When I say no disorder, no irreversibility. So if there is no irreversibility, then there is no entropy transfer. So you can call that as work transfer, energy interaction with no entropy transfer. So that is work transfer. So if you have entropy transfer, that is heat transfer. If there is no entropy transfer, then that is work transfer. So energy is exchanged during work interaction, whereas both energy and entropy are exchanged during heat interaction. Very, very important. So in work transfer, there is no entropy transfer. In heat transfer, you will have both the transfer of energy as well as transfer of entropy. Okay. So this is something which you should keep in mind always. This is very simple. Entropy transfer associated with mass flow. Say suppose you have an open system. Say suppose this is a system that you can consider. Some amount of mass is entering into the system and some amount of mass is leaving the system. Okay. So this is mass leaving the system. This is mass entering the system. I for inlet, E for exit. Mass entering the system, mass leaving the system. Okay, and if this mass is entering with a fixed entropy S, so ms is the entropy that is entering into the system, and mes will be the entropy that is leaving the system. That is entropy transfer associated with mass flow. That is very simple. Okay, so that is your entropy transfer associated with mass flow. And this is very important. Entropy generation in a closed system. And after this, we will talk about entropy generation in an open system. So when I say a closed system, so in a closed system, we usually take a cylinder piston arrangement. There is no mass transfer. There is only energy transfer there. Just like we studied before, your entropy of a closed system can be increased by two means. One is by heat interaction. Lot of examples we have seen. The other one is the irreversibility or the dissipative effects. Okay, so that is why they have said the work is dissipated into internal energy increase. Okay, so that causes the irreversibility. So when you talk about the entropy change, so the entropy change can be because of the entropy change DES or DIS. The change in entropy because of the external effect, or the entropy change because of the internal irreversibility. This external effect could be will be the heat transfer that is taking at the boundary. Okay, whether heat is entering the system or heat is leaving the system. If it is entering the system, it is positive. Leaving the system, it is negative. So this DES can be written as dq by t. Okay, and this DI is nothing but the irreversibility, internal irreversibility of the system. And we know that from Clausius inequality, this ds should be greater than or equal to dq by t. Otherwise, dq by t. So if it is a cycle, this ds will be 0. So dq by t, cyclic integral of dq by t will be less than or equal to 0. The reverse of it we have done here. So ds will be greater than or equal to dq by t. What is the meaning of this? ds is equal to dq by t. So they are saying ds should be greater than or equal to dq by t. Okay. So this ds greater than or equal to dq by t is possible. It is greater than, if it is greater than dq by t, then it should be added, something else should be added with this dq by t, and that is your dis. So that dis is greater than or equal to 0. Okay, and so they call this dq by t plus this dis. This dis is what is called as entropy generation. This internal irreversibility cause is what is called as the entropy generation. So you can put it the other way around. This ds is nothing but delta s of the system, the total system. This dq by t is the boundary phenomenon which is happening external to the system. So that is the entropy transfer at the boundary. And this is the internal irreversibility which is called as the entropy generation. Okay, and so we are taking, so there is one reversible criterion and there is a irreversible criterion. So for a reversible process, when you write the first law, dq is du plus dw, and for the reversible process only you can write it as pdv. That also you should keep in mind. Integral pdv, we have already done this before. In case if you have forgotten, you can recall this. This W equal to integral PdV is applicable only for a closed system, that every one of you will reckon. But what you should also remember is this W equal to integral PdV is applicable only for a quasi-static process, which means I'm talking about a reversible process. That is very, very important. This W equal to integral PdV is applicable only for a reversible process. So for an irreversible process, you cannot write W as integral PdV. Okay, that is something you should keep in mind. So that is why here we are replacing dW with PdV. Here for an irreversible process, we can't replace it. You have to write it as dW. In fact, this dW is inexact. Okay, so dur is equal to duy. The change in internal energy, that is going to be the same irrespective of whether it is an irreversible process or a reversible process. Okay, and so what you can write is, because this dur is equal to duy, dqr minus pdv will be equal to dqi minus dw. Okay, so you, in the other way, you can write it as dur equal to dqr minus pdv. And here you can write this as dui equal to dqi minus dw. Now, because this dur is equal to dy, the right hand sides can be equated, and that is what is done here. dqr minus pdv is equal to dqi minus dw. And if I divide this by t everywhere, and if I rearrange, if I take this pdv to the right hand side, what I'll get is dq by t for a reversible path is equal to dq by t for an irreversible path plus pdv minus dw by t. And the most important thing which I want to show here is this pdv minus dw. This pdv is the work done in case of a reversible path. This dw is the work done in case of an irreversible path. and the difference is what is called as the last work, and this work is lost, wasted. Okay, this is the amount of work that has been wasted, that has not been utilized, that has not been extracted because of the irreversibility. Okay, so this is called as the last work. Okay, and that is because of this irreversibility, that is because of this entropy generation. Okay, so just a minute. So this is your last work. PDV minus dw is your last work. I have failed to write a couple of equations here. Okay, just one more step here. So this is dq by t. So from here, this dq by t for a reversible path minus dq by t for an irreversible path is equal to what we call as the entropy generation. So this can be written as, this can be simply written as S2 minus S1, because that is the definition of change in entropy. Change in entropy delta S is dq by t for a reversible path. So you can replace this with S2 minus S1, and you can replace this with integral 1 to 2 dq by t, and this is for an irreversible path, and that is equated to generation of entropy. Okay, and this is your entropy change. Okay, this dq by t between the limits 1 to 2 over the integral, this is what is called as entropy transfer. So this is your delta S transfer, and that is your entropy generation. Similar to this equation, you see delta S of the system is equal to delta S transfer plus delta S generation. So that is what we get here. Okay, so because we are talking about entropy generation, this entropy generation is nothing but entropy change of the system minus the entropy transfer that takes place in the system. Okay, so in other words, your entropy generation is the last work. Okay, the last work divided by temperature. Okay, so PDV minus dW. So that is the last work divided by temperature. So that's PDV minus dW is also a form of Q, right? Energy. So Q divided by D. So that is what is called as the entropy generation or entropy production. Okay. So that is for the closed system. Okay. And for an open system, so in a closed system, we just had only one balance, which is your energy balance. In case of an open system, you have three equations that needs to be balanced here. One is your mass balance. So I have just, for want of time, I have taken it directly from PK Nag. So the first equation is the mass entering into the system. So m dot I, summation of I over m dot I minus summation of E over m dot E. So no matter how many mass entries we have and mass exits we have, the difference between mass entry and mass exit will give you the net mass transfer rate. Okay, that is equal to rate of mass accumulation in the system. This is similar to what we have written before. M dot in minus M dot out is equal to M dot stored. So that is what is written in this particular form. So that is your continuity equation. We call it as continuity equation or the mass balance equation. And this is nothing but your steady flow energy equation. Summation of mi into h plus v squared by 2 plus gz at I minus m dot e h plus v squared by 2 gz at E plus q minus shaft work into dou E by dou T. This should be equal to dou E by dou T, which is nothing but the energy flow rate, E dot, rate of energy accumulation in the system, in the control volume. Okay, so that is your energy balance. Similarly, you can also write entropy balance. So in the previous case, when I talked about the entropy associated with mass flow, so how much amount of entropy is entering into the system? That is m dot I into Si. Entropy that is leaving the system, m dot E into Se. So this is the net rate of entropy transfer. Just now we saw delta S of the system plus delta S of transfer is equal to entropy generation. Okay. So this fellow m dot I Si minus m dot E Se is the entropy transfer, and this q dot by T is nothing but your entropy of the system, entropy change of the system. And this delta S by dou S by dou T is the rate of increase of entropy of the control volume. So that should give you the entropy generation. Okay, so that is your entropy generation. So your entropy generation is so here they have given it in terms of the inequality. So S dot generated is dou S by dou T. So they are bringing all these to the right hand side. Okay, so that gives you the entropy generation in case of an open system. So if you have m dot I Si amount of entropy entering into the system, and you have m dot E times Se is the amount of entropy that is leaving the system. I'm just showing you one. You can have multiple. If there are multiple things, then you have to sum it up. That is what this summation is all about. Okay. So that gives you m dot I minus Si minus m dot E Ac. So that is the net rate of entropy transfer. And if you have heat entering into the system, say this is Q dot, and say the surface temperature of the system is T. So if heat is entering into the system, and if the surface temperature is T, then Q dot by T is the entropy transfer owing to the heat transfer rate. Okay. So this is entropy transfer owing to mass flow. This is entropy transfer owing to heat transfer. So both of them are entropy transfers. Okay. So in this case, everything in this particular equation, everything on the left-hand side accounts for entropy transfer. Okay. And this fellow stands for entropy of the system, rate of increase of the entropy of the system. So that is partial S divided by partial T. So that is your delta S of the system. So S dot generated here is equal to delta S of the system minus delta S transfer. If I go back to the slide, you will be able to understand this. So we have seen that delta S of the system is equal to delta S transfer plus delta S generated. Delta S system is delta S transfer plus delta S generated. So because we want to find delta S generated, it is delta S system minus delta S transfer. So that is what we have here. Okay, so this is entropy generation in an open system. So what is this entropy generation? The entropy generation is happening because of the irreversibility. Okay, so that is the important thing which you should understand. Okay, so with this, the explanatory part of your entropy is over. So with this part of your fourth unit, half of your fourth unit is over. The next one is availability and irreversibility, which we'll be doing later on. Okay, and we will solve a couple of problems here, and all these problems once again I have taken from PKNAG. Okay, so it's 3:23 now. So before proceeding to the problem, I just want to make sure if you guys have followed this. So were you able to understand it? Or what is the difficulty in understanding this? You can let me know. Either everyone should have understood it, or it is like none of you have understood it. And probably the second one seems to be the correct answer. Kaushik, everything clear?
Yes, sir.
Really?
Yes, sir.
You really listened to what I said?
Yes, sir.
It is really amazing that you guys have understood. Okay, so if that is the case, so let's proceed with our example problems. See, till last year, this entropy will be a part of the third unit. Okay, entropy and exergy and availability, this will be a part of the third unit. So usually students will study the second law of thermodynamics up to refrigerator, heat pump, and heat engine. And surely one question will turn from that, and another question will be either from entropy or from availability. So they won't touch this part at all. And it is true that this part, entropy, is a little bit vague. Unless or otherwise you follow very closely, it will be really difficult for you to understand. I can very well understand that. Sometimes it is a little bit tricky even for me when it comes to entropy. So I'm pretty sure that you guys will feel that difficult, but no other go this time around. This entropy is um, separately given as the fourth unit. So you should concentrate on entropy. There is no other way. So that is why last class we have seen, I think, around 4 or 5 problems. So this class also I have taken some 4 problems. Even in my regular classes so far for the previous batch, I have solved the examples which I'm going to show you now. Okay. So uh, it is possible that uh, it's not possible. You will get a question from here. You from this entropy. You will surely get because it is given as a separate unit. So you should concentrate. Okay. The next unit is very easy. The last unit is very easy. We can do that very quickly. That is the easiest portion of the thermodynamics course. So fifth unit is very easy, but fourth unit you should concentrate more on this entropy part or the exergy and availability part. Exergy and availability and irreversibility, it is possible only when you know entropy. Only after studying entropy generation you can go to availability. That is why this part is very important. Okay, so if you have doubts you can ask me privately also. If you are a little bit shy in asking this in the public domain, you can ask me privately also. Okay, so please concentrate on unit 4 if you aim to get very good scores. Okay, so example 1, water flows through a turbine in which friction causes the water temperature to rise from 35 degree to 37 degree. If there is no heat transfer, how much does the entropy of water change in passing through the turbine? Okay, and you can assume the process to be a constant volume process. I have failed to add that in the question. So this is a constant volume process. Water flows through a turbine in which friction causes the water temperature to rise. So there is an irreversibility which is causing the temperature of the water to rise from 35 to 37. So it's a very simple question actually, a very simple 2-mark question. So this 35 degrees centigrade happens to be your T1, and this 37 is your T2, and you have to assume this process to be a constant volume process, and they are asking you to find if there is no change, sorry, if there is no heat transfer, what does the entropy change? Okay, there is no entropy change directly because of heat transfer, but for a constant volume process, by definition we know delta S is integral dq by t, and heat transfer in case of a constant volume process is cv times dt divided by t, and you will end up getting cv times ln of t2 by t1. And just like you know cp value of air, you should also know the cv value of water. For water it is 4.18 kilojoule per kilogram Kelvin. So it is 4.18 kilojoule per kilogram Kelvin. So 4180. So that is cv value ln of t2. T2 is 37 plus 273. So it should be 300, sorry, 310. 310 divided by 308. So this is approximately 4180. Some people write it as 4.187, 4187. At least you should write it as 4180 divided by 310 divided by 308. Because there is an increase in temperature, this should be a positive value. Delta S will be a positive value. Okay, and that happens to be 0.0243 kilojoule per Kelvin. A very simple 2-mark question. And the key is it is a constant volume process. So for a constant volume process, you can use the formula directly and you end up getting the answer directly. And this is problem number 2. This is try to focus on at least on the problem side. 1 kg of water at 273 Kelvin is brought into contact with a heat reservoir at 373 Kelvin. When the water has reached 373 Kelvin, find the entropy change of water, heat reservoir, and the universe. So this is similar to the example which we had seen earlier, where there is a heat transfer between a finite temperature body and a reservoir. Okay, when you say heat reservoir, the temperature of the heat reservoir is not going to change. Okay, so I have a body. So this is a body which here they have said as 1 kg of water. And this 1 kg of water is at 273 Kelvin. Okay, I should have done it the other way around. So let me change this as 373 and let me call this as the source, which is the hot reservoir. Okay, which is at 373 Kelvin. Okay, and this is brought into contact with 1 kg of water, which is a body what is this body which is 1 kg of water which is at 273 Kelvin. What you should understand is the water has reached 373 Kelvin, which means the initial temperature of the body here is 273 Kelvin. The final temperature of the body, so Ti of the body is 273, Tf of the body here is 373. The initial temperature is 273 for water. The final temperature is 373 for water. What about the reservoir? The reservoir is at 373. The initial temperature is also 373. The final temperature is also 373. Okay. So this is what we saw in the previous class, the last problem of the previous class. One is body, the other one is a reservoir. So now if I want to find delta S of water, if I want to find delta S of water, I precisely know what is the initial temperature of water and the final temperature of water. So I can very simply write this as MCV or MCP times ln of TF by TI. This is CV or CP for both. For the liquid, CP, CV values are same. So mass is 1, CV is 4180, ln of 373 by 273. This will give you delta S of water. Okay. What about delta S of this hot reservoir, heat reservoir? So delta S of this source or heat reservoir. So if I write this as delta S of the source, so S for source, I have to write this as what is the heat that is lost by this reservoir divided by the temperature of the reservoir. Okay, because this reservoir is only giving heat to this water. Water is at a lower temperature. This reservoir is at a high temperature. So heat is supposed to flow from the high temperature body to the low temperature body. But how do I know the amount of heat that is lost by this body? So you should write one more equation where you say heat gained by water. So I'll write it as H2O. Heat gained by water is nothing but heat lost by the source. So here we are not able to estimate what is the heat lost by source directly, but it is possible to find the heat gained by water because I know the mass of water, I know the specific heat value of water, and I know the final temperature of the water and the initial temperature of water. Final temperature of water is 373, initial temperature of water is 273. CV value is 4180, mass of water is 1 kilogram. So this will give you the heat gained by water, which is also the heat lost by source. Okay, so it will give you a positive value, that is the heat gained by water. But when you substitute it, you should substitute it as minus because that is the heat lost by the reservoir. So that will be a negative value. And you have to add these two to get the value of the entropy change of the universe. That is subdivision A. Let's see how it is being done. Okay. So as I said, delta S of water, you can directly write it as MC ln of T2 by T1. Okay, so 4187 ln of 373 by 273 final temperature by initial temperature. This will give you delta S of water. So amount of heat absorbed by the system from the reservoir. Okay, so that is mc into T2 minus T1, which is positive. So entropy change of the reservoir is losing heat, so you put a minus here. So minus of Q by T, so you get minus 1.122. So when you add both, you should get a positive answer. Only then your problem has been solved correctly. So entropy change of the universe will be always greater than zero. So I hope now this particular doubt is being clarified. So when one body is at a particular temperature and you don't know the final temperature, then you estimate its heat and then divide by the reservoir temperature. When both the final temperature and the initial temperature is known, then you go for mc ln of T2 by T1. Okay. So now is this clear? Last class, I think Kaushik asked this question, like why we should not use mc times ln
Yes.
of T2 by T1 for oil also. Okay, in this case, and we treated oil as the reservoir there. So now here the reservoir is very small. So now is that clear to you?
Yes, sir.
Okay. So now subdivision B. So now what we are doing is then what they are asking us to find out is the same water is heated from 273 to 373, but how it is being done? First, it is brought into contact with a reservoir at 323 and then with a reservoir at 373. What will be the entropy change of the universe? So here you have 1 kg of water. So let me write it as 1 kg of water. So this is 1 kg of water and this is at 273. Okay. Now what happens is this water is first brought in contact with let me say a thermal energy reservoir, a heat reservoir 1, and then it was brought in contact with another reservoir, thermal energy reservoir 2. The concept is same, but when you substitute it, you have to be a little bit careful here. Okay, there is no change in the entropy change of water. This is going to be the same, mcp ln of final temperature by initial temperature. Final temperature is 373, the initial temperature is 273. So this delta S of water is going to be the same. If we think like that, then we will be making a mistake. Why we will be making a mistake? The water is heated from 273 to 373, not directly. It is done in two steps. Okay. So when you write delta S of water, let me take a blank slide here. So for delta S of water, let me say W, what is actually happening is when I say MCV ln of first final temperature by initial temperature is 323 by 273. So that is what is happening first. And then what we have is MCV ln of final temperature by initial temperature, 373 by 323. It is done in two steps. It is not done directly. So now if you find, there will be a change in the value. For that entropy change, you will have a different value. And for this entropy change, you will have a different value. Do you think so? You can try, but what you will find is you will get the same answer, because the value, the logarithmic expression, you can multiply within the ln, you can multiply, right? MCV is common. So within the ln, you can multiply and you can cancel out 323 and 323, which is simply ln of 373 by 273. So you will get the same answer for both delta S of water in both cases. So you need not split and write. Even if you split and write, you will get the same answer. Without splitting and writing also, you will get the same answer. But where you have to be very careful is, now you have got two reservoirs. One is the reservoir 1, the other one is the reservoir 2. And where you have to be careful is, the formula that you are going to use is Q divided by the temperature of the reservoir 1. So let me call it as RES1. Okay. You won't make mistake in this reservoir 1. In the reservoir 1, you know that the temperature is 323. So here you will not be making a mistake. But where you have to be careful is with this Q value. This Q value is between water and the thermal energy reservoir 1. So here your MCV won't change, but final temperature is 323 here. So it is supposed to be 323 minus 273. You should not mistakenly write it as 373 minus 273. Then you will be making a mistake. Okay, heat lost by the thermal energy reservoir 1 is equal to heat gained by the water from thermal energy reservoir 1. And because this is heat loss, this will be minus. So you will get a minus sign for this. So this will give you a negative value for the first thermal energy reservoir. So similarly, you have to do it for the second thermal energy reservoir also. So delta S of thermal energy reservoir 2 is equal to minus Q divided by temperature of the reservoir 2. So here you will have minus MCV, and here you may write this 373 correctly, but the next thing is minus 323. Don't mistakenly write it as 273. Then again you will be getting a wrong answer. So this fellow will also be negative. This will be negative and this will be negative. Only this fellow will be positive. So now if you add these three, you should get a positive answer. Okay, and this will be lesser than the previous one. So if you look at it, so for water, it is 1.305. In the previous case also, it is 1.305. Okay, so there is no change when you write it like this. You will get the same answer. But for reservoir 1, as I told you, it should be between 323 and 273. And here it should be between 373 and 323. Okay, so if you are careful here, then this question is very, very